Hello, it's James here. It's part 8 of openDog, the open source dog robot. As you can see, we've done quite a lot already on this. There's obviously 7 videos already, building and prototyping all of the mechanics, putting the electronics in, which we did last time, and this time we're going to actually write some code on the robot, at least for the initial setup, to get all those motors and encoders homed and get all those actuators in the right position so we can eventually build the kinematic model, and then we can control all of those joints. The only thing I've done since last time is built this wooden support frame to hold the robot up so I can mess around calibrating the legs without it falling over, and that's got 4 posts and it holds the robot up on the actual posts, which are part of the stationary part of the robot. Of course, one side of the mechanism moves, the other one is stationary, and those are offset, so we've got them in sort of diagonal configuration. Those 4 posts hold them up there, so that should hold the robot nice and stable so we can mess around with the legs. So before we can make the robot move, we need to do 3 things on the O drive calibration. We need to set the brake resistance for regenerative braking on each O drive. We also need to set the number of motor magnet poles for each of those 12 motors so the O drive can control the brushless motors properly, and we also need to set the motor stator versus encoder position so that calibration doesn't have to run on every power up. Basically, we'll run it once and then we'll hard code those values, and then these encoders have Z indexes on them, which means on the power up the motor will just rotate to find its Z index and it will know exactly where it is. My robot has 6 O drives and each one controls 2 motors. Each O drive is supplied with a brake resistor, so these O drives will do regenerative braking, which means that basically when the motor is braking it will put power back into the battery to recharge it, which is quite good. If you're using a mains power supply, of course you don't want to force power back into it, but I'm using battery, so I'm setting my brake resistance to 0. However, we need to check we never overcharge the batteries. Currently there's 2, 1 on each side. There will eventually be 6 in total. So what we're going to do is just not charge those fully so that we can push some power back into them to keep them charged when there's braking on the motors, and we won't overcharge the lipos. So brushless motors are a bit special. They have 3 wires and 3 phases, and you have to energize each phase at exactly the right time depending on the motor stator position so it can push the magnets round. Now, some motors have Hall effect sensors in, and the motor drive will read those to work out what the position is so it can sync everything up. Some of the cheap RC brushless motor drivers don't have any sensing, but they use the back EMF that comes back off the motor coil to work out what the motor position is. And in our case, of course, we've got encoders, and those encoders are not only used for that motor magnet positioning, the motor stator positioning, so you can energize the coils at the right time, but they're also used for counting the position of the motor and keeping track of it. I'm using the O drive tool to configure the O drives, and that just plugs in with a USB cable and allows you to configure the parameters. So I've set the motor braking resistance to 0, and it looked like the motor pole pairs value is already correct. Now, I'm not going to go into too many details about the O drive tool because it's probably subject to change. It's changed completely since the early episodes I did with the early R&D on the prototype leg and the O drive, so have a look at the O drive website. The documentation is really good and complete, and you can get hold of that tool as well on GitHub. So let's talk about that motor calibration, the motor stator calibration against the encoder calibration. So if we don't hard code the offset, then the startup looks like this. So the motor goes beep, and then it should turn in one direction. It should stop and turn back the other way, and that allows the O drive to calibrate the motor stator position against the encoder. And the encoder's got 8,192 counts per revolution, so it's really high resolution. If we were to hard code it, then it doesn't need to do that anymore. All it needs to do is seek its Z position, which occurs once per revolution. So on startup, we just say to calibrate the motor, it will just turn a little bit, and that will be it. Now, I've got a few issues here because I've got the encoders attached, as you can see, to a piece of 8mm studding shoved into a piece of plastic attached to the back of the motor. That's what causes the encoder to move when the motor moves. Now, the motors are actually provided with a metal piece, which is what you'd normally put on the back of these motors for drones, and that's a proper aluminium, nice machine piece that goes on the back there, and ideally that's what I've used to put the encoder on. However, this has got a 10mm shaft on it, and the maximum hole in the encoder is basically an adapter for 8mm, so that's why I haven't used these. Ideally I'd turn these down in a lathe, which I will do eventually when I get a lathe, but I don't have one at the moment, so I've got this makeshift piece. The only slight challenge is the 8mm studding is slightly smaller than 8mm, so I don't think the encoder is gripping properly, and some of them have slipped and I've had to wrap tape around them to make the shaft bigger. So that doesn't seem very reliable. For now, I've also got 3D printed plastic pulleys. Eventually I'd like to upgrade them. I think they might slip against the shaft, and although it doesn't affect the encoder, in order to do so I have to kind of slacken the whole motor off to get the belt on. So this is okay for now, but it's not the best solution, and we really do need to keep that encoder in sync with the motor stator if we hard code it. Any deviation is going to cause the motor not to operate properly. So for those reasons, I'm going to manually run the full calibration on each startup, and we can call that from code until I've replaced those pieces with metal and I'm sure that the encoder is tied to the motor reliably. So now it's finally time to make the legs work, and I could just drive the motors, but we need to put a home switch on, which I fitted last time, but I didn't put on anything to press it. So now I've got these blocks, which are going to fit on here, and as this winds towards the end of the axis, of course it'll switch the switch. And that's also going to be right at the hard end stop, so if I overrun them, the motor jams and it doesn't break the switch off. So we need to set up a homing routine, which we discussed last time with the illuminated buttons on the control panel, which will be able to home each leg in sequence. And then once they're all homed, then we can actually give them proper position data. So why not use absolute position feedback encoders on the actual joints instead of home switches? Well, we could do that, but it would only be any use when we first powered the robot on to discover what the state of the robot was, what the leg position was, because basically the O drives still need that encoder coupled to the actual motor in order that they can energize the motor coils properly and use the brushless motor properly and know what the stator position is of the motor. So we'd still need those encoders coupled to the motor, attached to the O drive so that the O drive can drive the brushless motors. So for now, an end switch will do so we can get to a known position for that joint. We could put absolute position feedback on the joints in the future, but it has to be really accurate, and it's only going to function when we first power it up the same as the end switch does. So now I've modified my control panel code, so instead of the lights just chasing each one as you press them onto the next light, basically now when you press this one, it goes out until the home switch gets pressed. And first it looks for the home switch 0, which is that one for motor 0, and then it looks for the other one, so we'll press that, and then you can see the next light comes on, and then if we press that, it looks for the home switch over the other side to be pressed on motor 0 on that O drive, and it looks for the next one, which is around the other side, and then it will go on to do the actuators underneath. But we're probably going to boost the legs up and take the wooden stand out before we go and do those, and obviously we need to do both ends of the robot as well. And the code for that part's pretty simple, so essentially it's looking for button presses, and this is a state machine using if statements. So it's got a flag set to 0, so the first time you press it the flag is 0. It does a bunch of stuff here, which is basically a while loop looking for that home switch to be pressed, another while loop looking for the next home switch to be pressed. Obviously I need to put in the stuff to actually move and stop the motors, and then it increments the flag to 1, and that goes on to the other leg with the other buttons, and eventually it will do the actuators underneath, but I haven't done anything for those yet. So now I've put the belt on so the actual motor can drive the thing that pushes the end switch. So if we press the first button on the control panel, we should see the first motor calibrate. There it goes, so it's going to spin one way and then the other way, which doesn't take too much longer than just looking for the Z position, so we're pretty happy with that for now. The next thing it does after the calibration is goes and presses the switch. And then it stores that switch position as a variable, and it backs off exactly 2 revolutions. And that means we've got a known position for the leg, and you can hear the other one beeping, so now it's doing exactly the same on that one. There it goes, so we should see that homing on its switch. And backing off exactly 2 revolutions. So now those joints are in a known position and we know the encoder offset. So you may just be able to see that the next light is coming on the control panel. If we press that one, it does the other side of the robot. So it should start homing this motor and doing exactly the same thing. My control panel is divided into 2 halves. Of course, this is the one end of the robot and this is the other end of the robot. And of course, those are controlled by 2 different slave Arduinos. So this one's now ready to do the actuators underneath, which we'll come to later. And the other one is still waiting for me to do the first actuator. And this end, as you'd imagine, is exactly the same. So if I press this button, it starts to home this one. And then it goes through doing this side and then goes to the other side once it's done. So, of course, I've added in the O drive stuff to the code. So we've got the O drive library being used here. We're using both of the O drives here on the 2 UART serial ports. We will have a third one for the undercarriage actuators that will be on a software serial. But for now, they're on both UART serial. So we've got 2 O drive objects called O drive 1 and O drive 2. In setup, we set up the current limit, which is currently set to 10 amps. And we set the velocity limit there to 1100. So that's pretty slow and pretty low power. We can turn that right up to 70 when the time comes, and that does 2 of them for each of the ODE drives that are connected to the 2 UART serial ports. Once we've pressed the first button, we need to do the motor calibration, so it puts it into the motor calibration state, then it looks for the offset calibration, and then it puts it into closed loop control mode. That means we can control it and it's got holding torque. Now if we had hard coded the motor stator position versus a Z index, we could scrap this one and just do a Z encoder index search, so it'll be a little bit quicker. There's only one line of code we need to change once we've done that calibration in the future. The only thing I did change was about the home switches, so we've now got this filter here. So I found because I'd used unscreened cable, I had quite a lot of phantom home limit switch presses. So basically what it does is resets the clock if the home switch is 1, which is when it's not pressed because they're input pull up, and when it's 0 it checks that the time has expired, which I think is about 50 milliseconds at the moment, and that filters out any jitter on those lines. It's a bit nasty really, I should have used screened cable, but this seems to work perfectly well. So after that of course it sets the velocity on the motor to 10,000, and then when the home switch is pressed, we're using a while loop to monitor that switch. It goes off and stops the motor, does a 300 millisecond delay. Then this code here is for basically reading the offset position from the encoder, or at least reading the encoder position. And then we do a set position using the encoder counts, and we do that for 2 revolutions. So it's using the offset position and then taking away 8192 encoder counts per revolution times 2. And that means it actually backs off 2 revolutions. And then it goes on, of course, says that it's going to do the next motor. Some of this comes out to the serial terminal for debug, and does the other axis, and does that 4 times for the 4 motors. So now the legs have all found their known positions, I've written an extra bit of code that turns both orange lights on, and that's before it gets to the white lights. And if I press them, it should lift the whole robot off the stand. So it can definitely lift itself, and it's still on hardly any power. That holding torque is still on about 10 amps. It lifts itself perfectly well. We can go right up to 70 amps and 48 volts instead of 24 volts. And I'm not even running full speed there, nowhere near. It's about 20 times slower than the top speed I've had on about 30 amps and 24 volts. So it's just enough to get it off the stand. Only just though, you'll notice it could do with going a bit higher really. Anyway, now we can lift up each leg individually and go and bring them into the limit switch, which actually brings them in, which is why I've removed the stands. And then we can deal with homing those actuators. So this is still actually running just on 1 battery at the moment. Now I've got a clamp meter here which measures up to 100 amps DC, does AC and DC, and all you do is put this round the cable. It tells you how much current is being drawn. So I'm going to have to do it like that. It's upside down. But what we've got there is, so 0.42, so 400 milliamps. If I turn 1 motor, yeah, that goes up to about 1.5. And if I let go again, it goes back to 400 milliamps. And that's just holding power basically for 8 motors. So it's not really drawing much power at the moment. So I'm using the mic on the camera now instead of the tie clip mic, because the cable from that picks up all the motor noise like a big aerial. So now we're going to get ready for the next stage of the homing. So basically what we're going to do is pick up this leg and then go and home it with the actuators that live under here. So first of all I'm going to stick a piece of wood in, because it can't stand on 3 legs any more than your dining room table can. Obviously if it's moving slowly I'll have to lean over in order to pick up its feet, and if it's going fast I'm not sure what will happen. With Robot X we found we could just pump the feet really fast. We didn't really have to pragmatically lean mass side to side, and it stayed up okay, so I'm hoping this will be the same with 4 legs. So next I just press the control panel button that's now gone white, and it should pick this leg up, as you can see. Then you hear the beep, and that's the motor calibrating, so you should be able to see this motor turning. There it goes. And then it should bring the actuator in until it hits its home switch, which is up at this end. And then it puts it back a set distance again, and then it brings the leg down again. There we go, so we can take the wood out now. And we can do the other side as well. It's not too bad just to hold up, I'll just hold it here. Just do the same thing to this side. So that's picking the leg up. Then we should see the other motor turning and calibrating. And moving in to hit the home switch, which is up at the other end on that actuator. and moving it out a known distance and putting the foot back down on the ground. So the other end of the robot's exactly the same as that. It's exactly the same code, running the other slave Arduino to control that O drive. So I'm not going to bother going through the code. It's pretty much the same as the leg homing. It's doing exactly the same thing, just with different switches and addressing a different O drive. But the code is on GitHub if you really want to go through it. So the next thing we need to do is control those two slave Arduinos from the master Arduino so that we can control the whole robot in one go and control all 12 motors. So let's think about what we actually need to do. So far we've got a transmitter with some joysticks on here, and this was used for testing in the early episodes. Check back on those to see this in action actually controlling one leg. And that's got a Bluetooth transmitter in, and that sends data to the master Arduino that sits in here. And that master Arduino is eventually going to calculate the kinematic model, so it's going to take these joystick motions for the 6-axis and turn that into XYZ motions for the legs, and we're going to do that in the next video. Then we've got two more Arduinos that act as slaves. Those are the ones we've been putting code on in this episode, and they actually control two O drives. So what we need to do is build a comms model that sends data from the master Arduino to the two slaves. Essentially there's a serial relays that send that joint position on and actually control the motors. So this is the code that's currently running on the master Arduino inside the dog there. So basically we're using Bill Porter's Easy Transfer library, and that's to send data from the remote to the master Arduino, and eventually we'll use that same library to send the data onto the slave Arduinos. Basically we've got the LCD there on both the remote and the dog, so I'm using the Liquid Crystal library, and this is all the setup for that. Now the Easy Transfer library involves declaring data sets. We've got one for receiving from the remote, so this is all the menu buttons and these are the sticks. And we've got one for actually sending data back. So of course we're sending data back to the display. The remote acts like a dumb terminal, so the mode there is actually being set on the code that we're looking at now, which is running on the dog. And the receiver there is just getting that data and displaying it, so it's tracked on the dog. It's also displaying a count every time the code loop goes round, so we can see that the code is running, and that is also displayed on the dog as well, just for completeness essentially. So we've declared these data sets with names we can read, so the send data and the remote data, and we're running the code loop every 20 milliseconds. So that's what this piece of code does here. So we've got our count adding up on every code loop, and that's being put out to the display on the dog, and of course it's actually sending that data back to the remote as well. This is to do with the menu tracking for those modes, so it adds one to the mode every time I press one particular switch and takes one away when I press the other one. And at the moment we're just writing out that serial data for the sticks to the screen and not doing anything more with it. So if we open a serial monitor, we can see that we've basically got 6 pieces of data there. The first one being the right stick for the left-right action, the right stick for the front-to-back action, and the right stick for the twist action. So each of these joysticks is 6-axis, and the other side is exactly the same. So the next thing to do would be to write the kinematic model, which will sit in here taking those stick positions. That piece is going to happen next time, but for now we're just going to bodge some numbers and write another set of Easy Transfer data sets that send that data onto the slave Arduinos. So the first thing we're going to do is make a data set on the master Arduino, and that's going to send that data onto the two slaves. So now on our master Arduino we set up two more objects called ET3 and ET4. Remember, the first two are for sending and receiving to the remote control. And of course one of these is for the first slave and one is for the other for the front and back of the robot. We've also set up two data structures, slave 1 and slave 2, and I'm calling the joint axis hip. And hip for each side of the robot, which is the actuator that moves the legs underneath the robot, the undercarriage, and then shoulder and elbow, which are the actual joints on the leg. I would call it like sort of another hip and a knee, but basically they point the right way for shoulders and elbows, so that's the easiest way to remember. And I've given those easy names to remember: my data back and my data front, which is again for the back and front of the robot. We then attach those to the serial ports on that one slave Arduino, serial 1 and serial 3. And remember that that Arduino Mega has 4 serial ports, and numbered 0 through 3. And these are the actual wires that attach to the two slave Arduinos, for the front and for the back. So right at the bottom of the code, our transmitting data sets. I'm transmitting the 2 right shoulders and the 2 left shoulders, and no other axis at the moment. And I'm actually taking the remote data, the right hand twist stick, and I'm scaling that from 0 to 1023 because it's 10-bit analog to digital converter to, in fact, minus 50 to 50. I'm doing that for all of the axes. And minus 50 to 50 is actually the length in millimeters, which is sort of not quite the maximum travel, but pretty much the travel, for testing at least, of that actuator. And I'm not going for sub-millimeter accuracy, this is going to transmit integers, but we are doing something on the other end that will give us sub-millimeter travel. We're then doing ET3 and ET4 send data that transmits that data to the two slaves. So now we're sending that data from the master on two different serial ports, and we're going to receive that on the two slaves. So now we're on the first slave Arduino that controls the back of the robot, and both of them are very similar. Of course, it's practically identical code. So we've defined another data structure for easy transfer, which has got those same axes in it, and we need to make that identical so that we can receive exactly the same data. And this one has a slave data structure called my data back, because it's the back of the robot. We're then attaching that data structure to the first serial port, and this is the same on both slaves because they both have serial 1 free. Now, as a test, I'm doing this right at the top of the code, right at the top of the main loop here, and we're doing an ET3 receive data, which is receiving that data set. And basically we're going to write out both values to the screen, which are the shoulder left and right, and I'm also doing some filtering. So if you remember in part 3 of the series, I did a filter that smooths out those values and makes them really nice. So if we scroll to the bottom, we can see we've now got a function that basically does some smoothing. So check out part 3 to see how that works and what the results are. But basically, if we open a serial plotter here, we should be able to see a nice graph getting plotted. And if I twist the stick here, now both the values are the same, so you can't see very much. They're both overlaid on each other for both shoulders, of course, because it's the same value from the same stick. But you can see my stick value, that's minus 50 to plus 50 in green, and you can see my nice red value there, which is nice and smooth, and that's the actual value that we're going to give to the actuator. So remember, data comes from the remote control, those stick positions, the 6 axes and all of the buttons, and that's sent via Bluetooth over to the master Arduino. We're going to run the Kinematic Model on there that calculates all the leg trigonometry, calculating all the angles back to actuator lengths. We're skipping that out for this time, but for now I'm just patching some numbers through to the 2 slave Arduinos that actually drive the 2 ODE drives. So there's a few funny sounds there. The main sound you can hear is the 3D printed pulleys and the belts running on them because they're not quite aligned. I think I actually hit the end stops on one of those demos, but also the conduit maybe makes a sound, or there's something clicking there somewhere. Might be that. But it is also the first time it's actually moved its legs fully since I've assembled it, so I guess there's still a few things that are settling in. There's possibly some creaking between plastic and metal bits that need tightening up, and we'll have to go and sort all that out as we go and activate the other axes as well. So the code for that looks like this. We get to the end of the homing where we've put the legs straight after homing the undercarriage axes, and then we set the flag in the state machine to 5. So the next part only happens once the complete calibration is complete and all the homing is complete. If obviously the Arduino loses power, we have to go back and do the calibration again anyway. So this will only happen once that calibration is definitely complete on each power up. So the first thing we do is receive the data, and of course this only happens once the homing is complete because that's the only situation under which the flag is set to 5. This is the same code that I showed before, receiving that data. I'm still typing it out to the serial terminal for diags, taking that filtered value. We're then multiplying the filtered value by a number of encoder counts per revolution to get the millimeters to turn into encoder counts, and that takes into account the gear ratio from the motor to the ball screw, which is about 2.14 something, and then we're making a home value, and that home value is using the value that the leg axis moved to get to its arbitrary middle position, and it's making a new home taking into account the offset as well, and that's called home to home and home for home. So we then use those values plus or minus the stick value in millimeters, now in encoder counts, which is then centered around 0, so that actually makes the offset and causes the actuator to move. So basically, once the homing is complete, the leg should stay in exactly the same home position until we wiggle that stick, and then it moves it plus and minus. And all of this code is pretty temporary. Once we've done the kinematic model, we'll actually have the correct amount in millimeters to get to the joint angle, and then that will be the final solution. So eventually we'll set some constraints on each ball screw using that home position so that they can't run their end stops, and obviously that will count the encoder clicks. The O drive knows where this is exactly, so if we just put in code never to go past a certain position, then that will be fine, and the O drive will never hit its end stops. So of course on each power up, the two slave Arduinos need to use that control panel. They need to do the homing sequence to get all of those home positions and calibrate the motors, but once it's powered up, that's it. I can then reboot this one, the master Arduino, multiple times as I build the kinematic model and experiment with gates and so on, without having to recalibrate these every time, because of course these will keep power and they don't need to be rebooted. So that means I can just keep flashing the master Arduino and I don't have to do the calibration every time I change the code. So as I've said, some of that code is temporary, particularly on the slave Arduinos, and of course the master doesn't have a kinematic model yet. I am putting the code on GitHub as I go because it is a truly open source project. The CAD is up from last time, the complete assembly. So if you want to build one of these, and I don't recommend you do yet, you can, and you can also sell them or modify it and sell them as long as you publish the source. Alright, so that's all for this time. Don't forget these projects are funded through Patreon, so have a look at patreon.com/XRobots and you can get access to some exclusive rewards, including a live stream with me and my videos early. Alright, that's all for now.